Good morning, good afternoon, and good evening, everyone. Thanks for joining us for another Data Engineers Lunch. Today it's going to be Data Engineers Lunch 94. We're very excited about this because we have a special guest returning, Angel. I hope I'm saying that perfect. Will Angel back again for upgrading Postgres for On-Prem and IoT. Great to have you back, Will. We're really looking forward to this. Let's just go through a couple of housekeeping items before we get started. The host for this event, Raul and myself. We are looking for speakers and sponsors for this event. If you're interested in either opportunity, please reach out to me at the email address below or contact us on our site. We are a part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is part of a larger group, a community of larger groups, all centered around data. You can find out more about these groups at the websites and Twitter listed below. So what do we cover here at our Data Engineers Lunch? If it's your first time, we generally cover everything surrounding data, everything from the ingress and egress of data and everything in between. We cover databases, ETL, data wrangling, and all the tools and processes in the data engineering world. If it's your first time here, please go ahead and introduce yourself in the chat, perhaps how you work with data, how you heard about this group, what you want to gain from this lunch, and any potential topics you'd like for us to cover in the future. Group rules, if you have a question, ask it. Will has mentioned that he likes questions throughout the presentation. So whenever you have a question, go ahead and throw that in the chat. He'll be having a look there as well, and I'll be monitoring it as well, and I'll pass it over to him. As I mentioned earlier, please be polite and courteous. And we do want this to be a community. We want to learn from each other. So please do share what you know with us. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. We'd like to thank our program sponsors listed below, also our organizational sponsors. Quick 15-second announcements. If you have any jobs, meetups, hackathons, conferences, or classes coming up, please go ahead and drop them in the chat along with a short description of what the event or class or whatever it is, just a short description about what's going on. So a couple data events coming up. We have our Data Engineers Lunch, obviously every Monday, our Cassandra Lunch on Thursdays. We will not be having a Cassandra Lunch this week, but we have the episode 5 of our Automate Jobs and Businesses with ChatGPT series. This may be on Wednesday or Thursday. Please stay tuned, to our YouTube channel so you know when that does go live. And you can also check out our events page at anant.us/events. And finally, our latest runbook is still out. This runbook has been available for a while. I think we'll leave it open for a little bit while before it stops being free. So if you haven't gotten your copy, please do so now. I'll leave a link to that in the description, in the chat, pardon me. And with that, I'll go ahead and hand it over to our speaker for this afternoon. Over to you, Will.
All right. Thank you for the intro, Akwi. And I will just say that all of the opinions here are my own and do not represent that of my employer, Excella, but we are hiring. So if you're interested in working with cool data people, consider joining us. Now, that said, let's go ahead and get started. So, hi, everyone. My name is Will Angel. I'm a lead consultant at Excella, and I help people solve data problems. I enjoy solving data problems so much that I make my own to do for fun on the weekends. So today I'm going to be talking about optimizing Postgres for an on-prem IoT installation, specifically my personal home sensor network. So today I'm going to be talking a little bit about the sensor network, the optimization challenge specifically, and why I needed to optimize Postgres, how I went about benchmarking Postgres to actually bring data to the optimization challenge, the actual optimizations I made, as well as the sort of order in which I like to approach database optimizations, and then finally the results. So if anyone has questions as we go, feel free to put them into the chat and I will keep an eye out for them. So let's talk about my home sensor network. So I built an IoT sensor network to monitor environmental data around my house. It's got a couple of custom sensor nodes that I made using off-the-shelf microcontrollers and sensors. And these send that data over the local Wi-Fi network to a Raspberry Pi which is running a custom Python web server written in Fast API that then saves that data to a Postgres database and then visualizes that in Metabase, which is an open source business intelligence tool that's great for building dashboards. So here's the system architecture. You can see we've got the IoT sensors. There are 3 of them right now, but I plan on adding more. They send that data over the router to the Raspberry Pi, where the Python web server receives it via HTTPS, saves it to the database, and then when I have the dashboard open, Metabase pulls that data from Postgres. So it's a fairly straightforward system. There's not a whole lot of back and forth and smart features yet, though with some of the humidity data I've been seeing recently, I'm definitely going to have to automate the dehumidifier so that it turns on and off based off this data. So as far as what this actually looks like, you can see on the left here, I've got one of the sensors with a 3D printed casing. And on the right, you can see the Raspberry Pi sitting in front of the router. So it definitely is not a proper server grade installation, but it serves my use cases. On the right here is the old dashboard, as well as pictures of the Raspberry Pi and one of the sensor nodes without the 3D printed case. So I put this together from raw components in this case. A couple of improvements since the last time I talked about this is that the nodes have the 3D printed enclosures, and that reduces foreign object ingress, or in plain English, it keeps the dust from getting into the sensors. I also replaced Power BI with Metabase to optimize the financial cost of the system, or in plain English, the real-time data streaming for Power BI is part of the premium plan, and given that this is for home use, I opted to not continue after the free trial. So it's all using off-the-shelf components and open source tools. So this is what the new self-hosted dashboard looks like. It's pretty great. With that context about the sensor network and how it works, let's talk about the optimization challenge. So the problem that I found over time is that the dashboard got really slow. That dashboard that I showed you could take 4 or 5 or 6. Like at one point, it didn't load for 10 minutes, which was just way too slow. So things like knowing what the maximum temperature was, or the max time, could take a minute and a half to just select the most recent data, which is really slow, and that was not fast enough. I basically stopped using the dashboards because they got to be so slow. So the question is why? And I had 2 hypotheses for why the queries were getting slower. The first is obviously that the data size was increasing. As I add more data to, the sensors collect more data, the database gets larger. I don't have any data retention and deletion policies in place, so it just keeps expanding, etc. And if there's more data, that means the query has to go over more, which means times increase. That makes sense. The second hypothesis is that the hardware, the actual system, was getting slower. Specifically for this Raspberry Pi, it's using a micro SD card for storage, and those can degrade over time with heavy write usage. So these were my 2 hypotheses going into this optimization challenge. First, for that first hypothesis that we're getting too much new data and it's slowing things down, I wanted to think about how much data do I actually expect to get. So each sensor node sends data every 500 milliseconds. So it waits 5 seconds, collects data, sends it, waits 5 more seconds, collects data, and sends it. And that's because the DHT sensors are not that accurate at high sampling rates. They're fairly low cost sensors. So we've got 3 sensor nodes, 1 record per 5 seconds. I expect about a little over half a row per second, or half a sensor sample per second. We multiply that by the number of hours in a day, minutes in an hour, seconds in a minute. That gives us almost 52,000 new rows per day. Not too shabby. I moved about a year ago and reset the database because I didn't need the old sensor data. And so we take our 52,000 rows per day, multiply that by 365 days in a year, and we get almost 19 million rows per year. That's not very much, but for a Raspberry Pi, that's not insignificant. So let's take a look at the actual data and compare that to our estimates. So we do a count of, select count star from raw data, and that tells us how many rows there are. And we had just under 18 million rows. So that's a little bit less than our sort of back of the envelope estimation, about 5% less. And that makes sense because, again, the code for the sensors, it's not every 5 seconds send data, it's send data, wait 5 seconds, send data, wait 5 seconds. So that suggests that the actual data collection takes about 250 milliseconds end to end, which for something that involves networking over Wi-Fi, that seems very reasonable. So one thing to note is that that query, just counting the number of records, took 75 seconds, a minute 15 seconds to do a count star or select star. That's not great. So the second question is, how much data on disk is this? How many megabytes, gigabytes do we have? And the answer is 1 3/4 gigabytes. So 1.76 gigabytes, which is not very much data, but the hardware is limited. The Raspberry Pi, it's a 3B plus model, and that means it only has 1 gigabyte of RAM. So that single table for that raw sensor data is now bigger than the memory on the device. So we're now dealing with kind of relatively big data for small computers like Raspberry Pis, because it no longer fits in memory. That means we start running into performance issues where you can't just put it all in memory and call it a day. Another thing to note is, like I said earlier, the micro SD card is several years old, so it could be starting to degrade. My understanding of how micro SD cards and flash memory tends to fail when it gets overwritten a lot is that usually results in full-on corruption, which would cause a full system failure as opposed to query speed degradation like this. So I didn't think that was the major issue. So it was one of the hypotheses, but I didn't think that the hardware is actually the problem here. So having sort of looked into that and decided that it was probably about the data size, I asked myself, what optimizations do we have that are available to fix this? And I did some research and came up with 5 ways to improve query execution times. First is write better SQL. If you don't have to, if you're writing bad SQL or writing, you're processing too much data, that's unnecessary and can result in slower queries. So the second is to organize the data better with indexes and partitions. That's usually one of the best strategies for managing a database. Third, optimize the data processing. Actually build a data pipeline to pre-aggregate data. When I'm selecting data in the dashboard, it's running those queries every time. And for historical data, once the data is in, it's not going to change. I don't have any late arriving records that'll show up days or years in the future. So once a day has passed, there's no reason why I shouldn't pre-aggregate it and then build the queries off that. So that was one approach I considered. Another one is to scale vertically, add more hardware. So the Raspberry Pi, it is an impressive little piece of hardware, but there are probably smart toasters out there that have more processing power. So it definitely is not the most high performance hardware. And the last option that I considered was to configure Postgres and really dive deep into the settings and try and optimize it there. But there's a lot of power there, as well as a lot of complexity and risk. So that was really the last thing that I wanted to do, because that's a great way to accidentally lose data, to bring down the system. There's just a lot more risk with that approach. So which one to start with first? There are a lot of different ways you can do those, and it's really contextual. So it depends on how things are, on what your actual bottleneck is and what those problems are. And the best way to actually decide is to use data. So I wanted to take a data-driven approach to this. And for that, I went with benchmarking. So benchmarking Postgres. The ultimate thing that I wanted to measure was how fast does my dashboard load? Now, because I didn't want to bring the actual data visualization tool, Metabase, into this, I decided to use this query as a proxy query. And this query, it takes all of it results in the average humidity per device per minute for the last 24 hours. So basically, with a data visualization tool, gives you a nice line chart of the average temperature, humidity, and light per device per minute for the last day. It's great. So I can take a look and sort of see how every room in the house has been going for the last day. So the query, the benchmark was 118 seconds, almost 2 minutes to run this on the last day, which it's not that long, but for a dashboard, if you ever sit for 2 minutes watching something spin, it's really not a good user experience. So the secondary measure that I wanted to take a look at was hardware utilization. Again, one of the hypotheses was that the hardware was the limiting factor. This is more applicable to other systems as well, where you don't have a fixed piece of hardware, but oftentimes, especially in a cloud context, we want to optimize our queries and database use so we can decrease the costs or improve reliability. So thinking about the actual hardware and how that's working is still important, even though I didn't think it was the major issue. There are a lot of different ways to look at hardware utilization. For this talk, I'll be looking at a tool called HStop, which is built, bundled with Linux. Previously, I've given some talks on logging and monitoring, and there are great tools like Prometheus and Grafana to measure both hardware performance as well as systems operation. So really getting that whole observability domain. So there's some very sophisticated as well as basic tools out there. So this is a screenshot of HStop. HStop is a tool for Linux for looking at system performance. And in this case, I am SSH'd into the Raspberry Pi. And there are a couple of things that I want to point out here. So I took the screenshot while I was running our benchmark query that I showed you. And here you'll note that Postgres, this Postgres process is using 97% of a CPU core. So there we can tell that Postgres is hitting some limits there with how it is using the hardware. And you can see here that we've got one of the 4 cores. It's a quad core computer. It's maxed out. So we're hitting hardware limits on running this query. Another thing to note is that we're not memory limited. So it's currently using basically about 1/3 of the memory on the Raspberry Pi. The swap memory is maxed out, but that's kind of a thing that happens when you have computers that have a lot of uptime, because they just keep putting things in swap, and there's really no reason for them to delete it ever. So because of this is interesting. Part of my hypothesis was that we were memory limited because, again, the raw table is now bigger than the memory, but we're not maxed out on memory here. So that's an important clue. A fun thing that I learned while putting together this talk is that HStop, if you have over 100 days of uptime, it gives you a little warning exclamation mark, because for Linux to apply kernel patches, it has to do a restart. So if you have multiple months of uptime, you start missing out on some of the security benefits of kernel patches. So it turns out radical uptime comes with some costs. So very, very interesting thing. So now that I've decided that it's probably not a full hardware issue, let's talk about optimizations. So the obvious thing is to write better SQL. The first query is getting the average temperature from the table. It processes a lot of data. You think about that, it's like, all right, select the average temperature across all the data. Well, that's going to have to process all of the data. And again, that's almost 18 million rows. It's not that much, but it's a small piece of hardware, so that is going to have to go through all the data. Now, if we don't actually want to know the average temperature for all time, we can filter out a where clause and get the data for the last 24 hours. So the second query is going to get the average temperature where the timestamp on write is within the last 24 hours. And that takes longer. Huh? Didn't we just say that selecting less data should make the query go faster? Because less data to process should mean that it's aggregating faster. So the question then is, why does it go slower when we select less data? And to answer that, we're going to go into Explain Analyze. So Explain Analyze is a Postgres feature and SQL feature that allows you to get the database to tell you why it's doing what it's doing and give you information about how much that's costing. So let's go through this. So this is the query plan that the Postgres query planner put together, showing how it actually executed it. One thing to note is if you just use explain, it'll tell you what the query plan is without actually running it. If you do explain analyze, it'll do that exact same thing, but also run the query and tell you what the output is. Do note, explain analyze will run your query. So if you use explain analyze on delete statements, it will run them. On a select statement, it runs the query and then throws away the data, but on a delete statement, it will run them. So don't use explain analyze on delete. So looking at this, we want to read this in reverse order to look at where it got the data and then what it did with it. So it's starting out with a sequential scan on the raw data table. And that means it's going to just go through the whole raw data table, row by row, and grab it all, and then move to the next step. Next step is aggregating it. And it took 50 seconds, 5,200 milliseconds to aggregate 18 million rows. That's a lot faster than I could do it by hand, but still it's pretty slow. And then it also gathered and aggregated that as secondary steps. So the two big ones here are it takes all the data row by row and then aggregates it and gives us our number. So that seems fairly straightforward. Let's move on to the filtered query that was slower. So we do the same thing. We have our query filtering for the last 24 hours, and we look, and we see that the sequential scan with filter is slower, significantly slower. I'm gonna go back. The sequential scan on all of the data, so just going through and getting all 18 million rows, it took 23 seconds. Going through with the filtering took 86 seconds, but it removed, almost 18 million rows. Because again, we're looking at about 50,000 rows per day. And you can see here that aggregating, in this case, 55,000 rows, took 33 milliseconds. So aggregating that last day of data, super fast, super fast. But the sequential scan to actually get all of that data took a lot longer than expected. And that has to do with how Postgres does input-output, because for the actual filtering, it has to do more work to compare that. Now, there's an interesting thing here. If looking up that data is what's taking so long, but the aggregations are very, very fast, that means that this is a great place for an index. Yep, inclusive sequential scan. So let's add an index, and just creating a default index uses a B tree by default, and that allows our query to filter on that column, which allows Postgres to use index scans instead of sequential scans. So an index scan is where Postgres goes, and for each of the elements, it actually looks them up in the index. And this is actually a lot slower on a per item basis. Apparently, some of the rules of thumb suggest that it's about 25% slower per row. But if you're able to ignore a lot more rows, that means that in most cases, when you're working on a small subset of your data, like less than 5 or 10%, it's radically faster. So how much faster is it actually? Let's see. So we've added our index. We're going to run the exact same query, and it's going to go way faster. So we went from, let me go back, 86 milliseconds down to, 86 seconds to 183 milliseconds. And you'll note that the aggregate time is, the time it actually takes to aggregate the data is basically the same, But that index scan, it's using an index scan now instead of a sequential scan. It can basically just totally ignore all the data that doesn't meet the criteria, that wasn't in the last 24 hours. So this is super fast, specifically 470 times faster than the previous query. So this is a huge speed up that is basically all the optimization we need. So let's go back to our original benchmark query. It's a little bit bigger. It's doing more grouping, it's getting more averages, and we're down to 813 milliseconds. So we've gone a whole lot faster by adding a single default index. And there's even more that we can do because there are multiple types of indexes. There are all sorts of interesting things you can do with like bin ranges. And so this is about as basic as it comes for indexing. So it's really miraculous that we get a huge improvement in performance with indexes. And so you can see here that you can see here that the index scan is down to 286 milliseconds, and that the most expensive thing now is actually the sorting that it does to get that last 24 hours. So results. Our initial benchmark query time was 118 seconds, and now it is under 1 second, which is a 128 increase in performance, 128-fold increase in performance, which is huge. So now all of the queries in the dashboard load in under a second. And so that overall dashboard time has gone from multiple minutes to a couple of seconds. There are a few secondary benefits here. So by just using the indexes and query filtering, I didn't have to write extra pipelines to pre-aggregate the data. I enjoy doing that, so I'm probably going to do it eventually anyways, but that's engineering time that I didn't have to spend on the weekend writing pipelines, so not too bad. I didn't have to mess around with Postgres configuration changes. There are a whole lot of ways where you can make Postgres even more powerful by updating the configuration, but that additional power comes with additional risks. And if you don't know what you're doing, and Postgres is really sophisticated and complex, or rather it can be, those database configuration changes risk system downtime, data loss, all sorts of weird, unexpected things. I didn't have to migrate away from Postgres when there are dedicated database technologies like ClickHouse that bring data warehouse style online analytical processing and like time series aggregation to whatever hardware you want. So something like ClickHouse is built for this use case of taking time series data and aggregating it. But Postgres is well known and very easy, so not having to migrate is always good in my book. And I didn't have to upgrade the hardware either, which is kind of a shame because I've got a very, very nice little small form factor, a Lenovo PC that I was all ready to upgrade to. And then I did the indexes and realized I don't have to. I probably will upgrade at some point, but again, one less thing to do right now, and the system is back up and performing very nicely. So, a couple of takeaways. Indexes can offer massive performance benefits, especially for queries that select a small portion of your data. Again, if you're doing bulk aggregations, so if I want to get the average temperature for all time, that's still going to take a while. But if I'm only taking the temperature for the last day or week, that's going to be a lot less than 5 or 10% of the data. So it's going to be much faster with an index. One thing to note is, in addition to Postgres indexes, most database technologies, including data warehouses, have some equivalent. Some don't call it indexes, some do partitioning. These are really important. At a previous company, I helped save $250,000 a year by adding partitions to a couple of data warehouse tables. So they're just, if you have indexes, even if you're using a data warehouse that massively parallelizes and can just throw computers at it, if you add the equivalent of an index, you can use a lot less compute, get things a lot faster, and then pay a lot less. So even if you're not having performance issues, you may actually be having performance issues that are just getting hidden by spending more on the cloud. So indexing and partitions are very important. Another takeaway is to use data to inform your system optimizations. If I had just gone off of my hunch, I probably would have just upgraded the hardware and then been confused when it didn't actually make it go any faster. So data is very helpful. Explain and analyze is your friend. It will tell you many of your problems, and there's a whole bunch of different settings you can use to increase how much it tells you and that kind of thing. It's really powerful when you start getting into larger analytical queries. Say you're joining a bunch of tables in a data warehouse. There, the query planner can actually give you, depending on what you're doing, you can take that data and import it into a graphical visualizer that will show you how the query planner is actually going through your data and looking at that. And then you can be like, oh, I'm doing all of this sorting, spending a whole bunch of time sorting or aggregating things before I need to. And that can really help you write better SQL that performs better. So explain, analyze, very helpful. Modern computers are amazingly powerful. If you're slow, it probably means you're not using them fully. I think Rahul said in the chat, it's rarely the hardware, likely software or user issue. So that is exactly right. That said, you can often throw hardware at things and make the user issues disappear for at least a while, but that gets expensive and is often unnecessary. And a bonus takeaway is that the best data optimization is pulling the data less. So if you have a dashboard and it's slow, enabling caching at the dashboard level will allow you to avoid hitting the database as often. So that's a great way to reduce the frequency of your problems. With that, thank you. If there are any questions, feel free to put them in the chat. But
yeah, like Will said, if you have any questions, please go ahead and drop them in the chat while we close out here with some housekeeping items. Again, we do have episode 5 in our Automate Your Job and Business with ChatGPT series coming out this week. Please stay tuned to both our YouTube channel, our no-code meetup, and our website, anant.us/event for any updates there. Let's see, any questions here? Okay, no questions. Final thing I wanted to say, our runbook is still available. It's here in the chat. If you haven't, please go ahead and grab that while it's still free and available. We should have a new runbook out for you soon. So please make sure you do grab that. With that, I want to thank you again, Will, for another fantastic talk. We love having you on. We are thinking about doing something special for our 100th Data Engineers Lunch. If anybody has any ideas, we're very open to that. Will and I were talking about that a little bit earlier. So we really do want this to be a community event for the 100th. If you have any ideas, please don't hesitate to reach out. We should have something fun for you guys then. Another quick note, we will be off next week, Monday, in observance of the Memorial Day holiday. But the week after that, we'll be back. We're excited to have you guys join us again then. And yeah, I think that's all we have. Appreciate everybody joining us or watching this a little bit later. Thank you all, and we'll see you guys in a couple weeks. Take care, everyone.
Take care, all.